So this is where we got to. It was this one, isn't it? Yeah. So the rate at which fluid flows, and we had a bit of a debate when I did this with the other group as to whether that should be negative or not. It's going out of the tank, so we ended up not making it negative, and we ended up needing to make it negative because of what we did at the end. So we've got the benefit of hindsight here. The rate at which the volume is changing is proportional to the square root of the volume, and we're not going to use the same constant. I think, did I get what there I used? The other thing I've got is a cylinder. So the volume of a cylinder is the area of the end multiplied by the height, or the depth in this case. And I note that it's got a constant cross-section. So that means that R is a constant. Okay, R is not a variable in this question. The radius is something that's not going to change. So when I differentiate this, that's a constant. So that's like differentiating 3x, it becomes 3. If you differentiate this, it's going to become that. And I want dH by dt. So that's going to be dH by dV, that one flipped over, multiplied by that one. And that works, doesn't it? Because the dV's cancel out. So dV by dt. Now, this needs to somehow become like this. So could someone suggest the first step I could take? I've got a V here, which I don't want. Have we got anywhere an idea of what I can replace the V with? What can I replace it with, George?
Pi r squared h.
Pi squared h, okay, right. Now, well done if you got that far, all right? Well done if you got that far. This is I said there was a nasty sting in the tail here. This is all square rooted. This is the square root of something times something else. And you may remember when we first look at square roots at GCSE, we say you can write that as something like that. The square root of h you can write as two separate square roots, and we do that so we can simplify it as 2 root 2. I can do the same here. I've got minus pi over 2 times minus c times the square root of pi r squared times the square root of h. Can you see what's going to happen now? What's going to happen now?
No, you're going to cancel out the 1 over pi r squared.
Well, I can't because that's under the square root sign.
Yeah.
Well, let's just think. Pi, constant. R, constant. C, constant. Pi, r squared, constant. Square root of that, constant. All of this is going to be a fixed number. In fact, you could write it as that, which is what they've done. So that was the sting in the tail. It was recognising that all of this maths here is a constant. It's not going to change. There's no variables in there. So you can just write it as some constant times h. Now it was negative because we wrote that as originally, this is something that's flowing out, so that it is decreasing. But that was the nasty trick there. Happens every now and then. You find that a whole load of stuff just gets wrapped up and we say, right, yeah, it's just some constant. So there we go. That was that question there.
So I have a question.
Yes.
Can you waste one of the other maths lessons for the other group so that we can have those conversations about whether it's negative or positive?
Well, do you know what, George? Sometimes we do. Sometimes you are the first group. It just depends on the flow of the lessons. It's always better to be the second group. believe me.
I want to have the conversation.
You want to be the okay.
George,
Well,
you're gonna do the debate side.
Yeah,
I actually think that's.
You like
I don't want to hear
debating,
Matty and Joe and Sasha battling it out.
well, no. It's no. Honestly, we're doing exactly. You're not missing out. We're doing exactly the same work. In fact, we're more productive because we're not wasting time. And some of that group, some of the group, they don't treat me with much respect. One of them particularly. Right. Anyway, mechanics. Now, I hope that you've watched the videos. I'm not going to go around and say, have you watched the videos? Have you watched the videos? But I put those 3 mechanics videos together to try and get us to the point where we can start today's lesson. All right? And so if you haven't, then A, this lesson is going to be quite hard for you, and B, get it sorted this weekend. I also owe you an apology, because on the pre-release information for the second mock, I said that there would be stuff on it on the content of those 3 videos, but I didn't mention friction, and I've said already that there'll be no friction on there, which is the thing we're going to come to probably next lesson. I can't find a good exam question that doesn't include friction. So we are going to have to include friction in that. So I'm going to have to just add that to that pre-release document. So just make sure that when we come to friction, probably at the end of today or next lesson, that you're keyed into that as well. Okay? So we are dealing with forces at the moment acting on things. Most of the things are particles, and we say that a particle is something which has a mass but has no dimensions. And in all of the examples, it was either a particle or a block, either sat dangling or on a slope. And I hope you got onto the ones on slopes. And the reason I've got you those books to have at home is that I like the way those books teach this thing, and they only cost £5. So have I not given you a copy of the book?
Yeah.
I have a few spare, so I did think there were some people who missed out. Right. Because the book talks very much in terms of, in these problems in terms of 2 steps. It talks about situations where everything is in equilibrium. And that's Newton's first law. If something isn't moving, it must mean the forces on it are balanced. So if you don't shove it, it doesn't move. That's Newton's first law. Or it might be moving with constant velocity. And if you don't apply a force, it's going to stay moving at constant velocity. Now you might think, well, hang on a minute, that doesn't happen in real life. Well, that's because there are forces out there, air resistance, friction. So, but in this theoretical modelled world, if you don't apply a force, it either stays at the speed it's currently going or it stays in equilibrium. So we're going to talk very much today about equilibrium. There's one example where we don't. We're then going to move on to the situation where the forces are not balanced. And when you have unbalanced forces, you get acceleration. And we use F equals ma to work out that acceleration. Well, we've done all this already last year. We did it for horizontal movement, so things pulling trailers and stuff like that, and vertical movement, projectiles being fired up in the air. So the only difference this year is the angle stuff. So we're introducing the angles. So I'm hoping that having done the video, you'll be able to have a stab at questions like these ones, okay? So these questions, these first 4 questions, all involve a particle, so 0 dimensions, being held by 2 strings, and there's a force in each of those 2 strings. The particle itself, although it has no dimensions, it does have a mass, and so there is another force, the weight of that particle, which is always acting vertically down. The difference here is that we've got an angle. So we're dealing with balanced forces today, that's what I'm going to call it, balanced forces, which result in equilibrium. And you may remember, I'm hoping you remember because you've watched the videos very recently, that when we deal with this, we resolve in different directions. When we're dealing with things like this, we tend to resolve horizontally and vertically, but I could resolve in any direction I want. If this thing is in equilibrium, if I resolved at an angle of 14.78 degrees, I'd still find everything was balanced. We don't, because that would be crazy. We choose sensible directions. So I'm going to resolve horizontally and I'm going to resolve vertically. And I've got two ways of writing this. I'm probably aware that last year I used a different way to the way I wrote in the video. But I hope you can see that it's the same. I'm going to use Newton's second law, F equals ma, and say, well, okay, if we're in equilibrium, there's no acceleration, so you've got the forces combined to give you nothing. So in this situation here, if I'm resolving horizontally, I've got a 14 Newton force pulling it that way, but I've got another force pulling it this way. It's the effect of that force going at an angle. And if you've watched the videos, you'll know that the effect of that force is T times the cos of the angle. I know the angle, so it's T times the cos of the angle. And those two forces are balanced, so they equal 0, which gives us no acceleration. It is just the same thing if we decide just to say forces going one way equal forces going the other way. Those two things mean the same. So I don't mind which way round, which way you choose to write it. This generally is the easiest way because it's the sort of a natural progression. But I'm just conscious in the videos I was starting like that and then sort of rearranging it. It's the same thing. The weight has no effect horizontally. The weight is at right angles, so it doesn't have any effect horizontally, so I don't include it in that calculation. So I can work out T, and we need to make sure we're in degrees. Okay? It's just two Jameses, isn't it, physicists? And when you get that value of T, round it to 3 sig figs, but store the exact value. Now I'm halfway to the end now. I've got my value of T, but I don't know the mass of the particle yet, and that's the other thing we want. So I'm now going to resolve vertically. And I'm going to go straight to here. I'm not going to write 1 take the other equals 0. I'm just going to say up equals down. If it's balanced, they've got to be the same. If it wasn't, it'd be moving up or down. It's not moving up or down. So force down is nice and easy. That's just the weight of the particle, mg.
You use 10, don't we?
Say so?
We use 10, don't
We use 9.8
Okay.
for G. Yeah, 9.8. Confusing, I know, for your physicists because we're used to using 9.81. Now the force up is again going to be the effect of this, because this force here at an angle is pulling it both this way and that way, and this is where I may vary from the physicists. Doesn't matter which way you do it. I'm going to say, right, the angle there is 40 degrees, so the effect of that force upwards is T cos 40. If you do physics, or if you have a good recollection of the relationship between sine and cos, you'll know that that's the same as T sine 50. It's the same thing. It's the same thing. So whether you do sine 50, because that's just the way you've done it in physics, or whether you work out the angle and do cos 40, doesn't matter. The sine of an angle is the same as the cos of 90 minus that angle, and vice versa. We came across that in that obscure sine A plus B question in a homework where you had to replace sine 40 with cos 50 or something like that. Okay, I know T, I know G is 9.8, so I can work out M. So just see if you can do the others once you've had a go at that one. Sorry?
Oh, never mind. I didn't know what that 25 degrees was. But
Yeah, so 25 is the angle. Yeah, so you've got to do a little bit of, you've got to work out a few angles in this one.
Yeah, I was just really worried.
Yeah.
Is that the angle? Really worried. It does sound good, actually.
So I'm hoping you got. I'm sorry, I'll give you a chance. So in B, you've got to work out some angles because you don't know the angles that we're after. Okay, obviously we can work them out. We're told a different angle, 25, but you should be able to work out the angles you need. I'm hoping for this one you've got 21.8 for T and 1.70 rounded for the mass.
Oh, I need to do this.
Is that okay?
Yeah.
I was going to say lads and balance as a question.
Sometimes I just do it.
I can't think in my head. What do I remember?
So with the second one, the two angles I need are this angle here and this angle here. So this is where all those parallel line rules that we learned come in. So alternate angles, Z angles, this is 25. And if that's 25, this must be 65. So those are the two angles we need when we're dealing with that force. I just realised I've drawn over what the size of the force is. It's 8 newtons, right. 8 newtons. We've got 25 degrees there, 65 degrees there. So when we're resolving horizontally, the effect of that force in that direction will be 8 cos 65, and when we're resolving vertically, it will be 8 cos 25. Can you sign on this one if you want to? So this is the key bit. If you haven't watched the videos, this whole idea of a force at an angle has an effect in the horizontal and the vertical direction, and we can work that out using trigonometry. That's in the first video of the 3. On C, so When you say with your arrow, what do you mean?
You know when you do like arm and then in the brackets you do the arrow that way? Like
Yeah, well, it doesn't matter actually, but yeah, I always, yeah, so what I'm basically saying is that way is positive. So I'll say it's, yeah, but it doesn't, because these forces are in equilibrium, it doesn't matter. We're just basically saying the ones going that way are going to equal the ones going that way. But yeah, I always do my arrow going that way. So I'm rounding all these to 3 sig figs.
Would you have to put the unit of measure for these answers?
So a force will be in newtons, and a mass will be in kilograms. So yeah, good point. Oh, that's not good. Another one there to try. Now I acknowledge that my attempt to use cos all the time falls over when you get to question 2. So that's why I've included that one. Just
What's going on with sneezes today? Thank you. Yeah, I'm very high.
It's always hard to judge the pace. I know James and James are probably feeling quite, well, hoping you're feeling relaxed about this. Although actually I thought friction was, that you'd sort of covered it all, but apparently we're doing it slightly differently, so it is, you are going to learn some new stuff, hopefully. I'm just copying these out of the book, so I'm hoping that. Okay, I'm assuming, well, I know that the book has used the exact value rather than 9.93, so always remember to store where possible. Again, indeed, you've got to work out some angles, haven't you? Yes.
If you're working out the left-hand side, so 13, then would it be cos 13?
So are you doing it horizontally or vertically?
Vertically.
So vertically, yes, you've got W going down and 13 cos 32 going up. If you know the angle, it's cos.
The right-hand side would be sin if I was doing sin.
Yes, that's right, and we don't know the angle there. Yeah.
Okay.
Could we talk about the bottom one? Because I think the bottom one is a little bit more complicated. Anyone want to ask a question about any of these? I mean, if you've watched the third video, you'll know that I just tend to start by working out all the angles, and I don't always need them, but at least I've got them at my disposal should I need them. And then I know I can just use cos. So the effect of that 7 Newton force horizontally is 7 cos 55, and the effect of that 7 Newton force vertically is 7 cos 35. However, I could also say this is sine 55 and this is sine 35. So if you don't know the angle you're after, you can use the sine of the other angle. So this is where this presents us with a bit of a problem, doesn't it? So resolving vertically up, I've got 13 cos 32 and, sorry, I misunderstood your question, Pat. I've got 15 cos x. Because I know the angle, so when I know the angle I use cos. They're the up forces and they're balanced by W going down. Now that doesn't help me at all because I've got 2 missing values there. I've got W and I've got X. So I'm going to now resolve horizontally. Are you okay? No, you've got something. Here. So if I now go horizontally, I've got a bit of a problem with my I want to know all the angles approach. So that's going to be 58. So the force going that way is going to be 13 cos 58. And it doesn't matter which way round you put these two things. It doesn't matter. So the force going that way is that angle multiplied by that force multiplied by the cos of the angle. The force going this way, I've got this problem. I could write 15 times the cos of 90 times minus x, which is fine. But actually, what I'm going to do is write 15 sine of x. So this is one of the few times when I have to use the thing that physicists use all the time, where they know the angle with the horizontal, so it's the sine of that angle when you're working vertically, or in this case, we know the angle with the vertical, so it's the sine of the angle when you want to know the horizontal. I could have put the cos of 90 minus x in there, could have done it. Would have got the same answer. So I get that sine x is 13 cos 58 over 15, and I need to shift sign that to get the angle. And the good news is that it's clearly an acute angle, so there's no issue with lots of different solutions. You just get, well, hopefully you get 27.3. So sine x equals that. So you shift sign that to get a value of x. 27.3. Store the exact value of 27.3 because you're going to need it up here. Once you know that x is 27.3, you can work out w, and w should come out at 24.3 newtons. So in this question here, I really wanted to know that angle because it would have been 15 cos that angle. But if you don't, but you know this angle, or you've got a letter for that angle, you can use the sine. Cos when you know the angle, sine when you don't know the angle, but you know its complement to 90. So this is the difference between last year and this year. We're still resolving vertically and horizontally. Forces at right angles still have no effect, but we've got angles involved. We have met forces at angles last year. We met them in vector questions. So you may remember that a vector, the vector I, is a vector of one unit in the positive x direction, and the vector j is a vector of one unit in the positive y direction. So this vector here, which you may remember I far prefer to write like this, is a force with a component of 7 in the horizontal direction and -9, so that in the y direction. So it's a force like that. And what that means is when you get forces written as vectors, it's so much easier. It looks horrible, but it's so much easier because I already know the horizontal and vertical component. I don't need to do sine or cos. And that means when we deal with equilibrium, like we are in part A here, I know that these forces must balance out because we're told that these three forces are in equilibrium. So that must mean that the horizontal components all add up to 0. So I can easily work out what P is. And it means the vertical components must all add up to 0 as well. So I can easily work out what Q is. So do that bit for me and then have a think about the second part. The second part is the only bit of this lesson where we're going to leave the whole idea of equilibrium behind. So when the forces are written as vectors, it makes the whole resolving horizontally and resolving vertically thing so much easier. Particularly if we're dealing with equilibrium, because we know the horizontal force is 0, so those 3 I numbers must add up to 0I, and the 3 J numbers, the vertical components, must add up to 0 as well. How do you do?
Bottom set is starting to really get me angry. It's too hard for them completely.
Well, that's why if you say did you do an art questionnaire or something? Just say yeah. Did you manage to find the factors? Did you manage to?
All they're doing right now is no step, almost everything, no sound. All the bottom set kids are just, and no matter what I'm saying on here, it's just doing my thing.
Just say. Did you manage to list the vectors of 24 or something?
They've got to that point. All of them seem to be able to do the factor bit.
There we go.
So we've got.
So that's a win. That's a win. We revised factors. Right, so P has to be minus 12 and Q has to be 3 in order for those to be 0. Then if you take away F3, we've no longer got equilibrium. So this is the first and only time we're going to meet that this lesson. It means the resultant force, just add the 2 horizontal components, add the 2 vertical components. So we're then asked, basically, what does that force actually look like? You know, in all the other questions, we've been given the magnitude and the angle of the force. They're asking us to work out that in this case. Well, we need to remember what that looks like. It looks like a force with a horizontal component of 12 and a vertical component of minus 3. That means it's going down. So that's the force. The length of that is the magnitude. We did that last year. Now this angle here is the angle with the horizontal. I'm going to use tan to work that out, but you've just got to make sure you answer the question. That angle isn't actually the final answer to part C.
Do you need to work that out?
You do need to work that angle out and then use it to work out the answer to part C. if anyone comes across a spare calculator kicking around at home, I lent one to someone the other day, and I can't remember who, and I'm now down to 1. So I'm not cross. I'm just back. So the force, the magnitude of the force is 12.4 newtons. This angle here is shift tan of 3/12, which is 14.0 degrees. But the question says the angle that it makes with J. Now J is a vector going in that direction. So the actual answer is 104 degrees. 104 degrees. Now that could be misinterpreted because of course J, you could have drawn J there. So why was it 104 degrees and not 90 minus 14? And this crops up every year, and the way I always explain it is I say you've got to imagine the two forces, in this case J and R, sort of starting at the same point and then moving in their respective directions. So the angle between them is the angle that they make. So that's why it will be that angle there, 104 degrees, 90 degrees bigger than the angle we calculated. It's not this angle here, it's the angle they make if they start at the same point and then move away from each other. Okay. When do we finish?
5 past.
5 past. Okay, so let's get one of these done. That is 5 past. It's 5 past. Don't be thrown with this one by the fact you've got that dotted line there. It's just an angle of, ignore the dotted line, it's an angle of 10 degrees there. So here we've got the slope problems, which again you will have come across in the video, second video, and the third one. And when we are dealing with slope problems, rather than resolving horizontally and vertically, it's much easier to resolve parallel to the slope, and you don't need to, that's understood to mean that, and perpendicular to the slope. The weight, which is, we don't know, mg, will always be vertical. There's another force here, that's the reaction force, you may remember, that pushes up, but that goes perpendicular to the slope. So we've got a few angles to work out here, haven't we? We've got an angle there to work out, an angle there to work out. We know that angle there is 10. So we should be able to work out that angle there. So just have a go. This is harder, isn't it? This is harder. It's a shame that we're sort of towards the end of the lesson. It's not ideal, but I'm going to quickly do this. So going up the slope, I've got the effect of that force. That force is 70 newtons, so that's 70 cos 10. That's pulling it up the slope. Pulling it down the slope is the effect of the weight. So that's mg times this angle here. Now that angle there is going to be, that's going to be 60, isn't it? That's going to be 60. So that's mg cos 60. And that allows me to work out the size of n. Going parallel, perpendicular to the slope, it's been a long week, r is going up. In addition to r, this force, although it's pulling almost going that way, it has a small effect, so it's going to be 70 cos 80, also pulling up. And then going down, I've got the component of this force. Now that's 30, so it's mg cos 30. I've just worked out m here, so I should be able to work out r as well. Do you want to see if you can finish that first one ahead of Tuesday's lesson?